Hello everyone again. Today is the starting of a new chapter. The chapter's name is Work, Energy and Power. After completing all the different lectures, such as till now, if you are going with the flow of complete learning of physics from the first chapter itself, we have started with the kinematics concepts. Then we went on to study the laws of motion, and after this, now we will understand basically the concept work, energy, and power. So maybe in the real life scenario, it may look similar, but in physics terms, every word has a different meaning here. We'll understand all of these things. This may be a big chapter. We'll understand each and every concept very clearly. So let us start directly. So this is lecture number 1 of work, energy, and power. I'm Samir Lawankar. So let's begin our discussion. Okay, so these are all the concepts which we will be understanding in this complete chapter. So majority will be working on work, kinetic energy, potential energy. Then we will understand the applications such as your collisions, etc., which is the ending of this chapter. Okay, so also a more generalized vector concept, that is scalar product, dot product, will be understood in this chapter. So just look very clearly, understand that concept very carefully, so that we can understand more deeply regarding this complete concept or complete chapter. Okay, so that thing being said, I won't go into course outline today. That will be done when the lectures go on. So let us start directly with the introduction of this chapter, which is work, energy, and power. Okay, so let's start with the introduction. Okay, so the terms work, energy, and power. So as I already explained to you, so basically, generally saying, in real life scenarios, these all terms such as work, energy, and power. Correctly. So power can be understood as something different, but generally in day-to-day life, we say that if I'm doing more energy and if I'm doing more work, that means I would have had more energy. Correct. So let us say if I'm doing a workout. So in a workout, generally what people observe, or what generally people have a feeling, is that if a person's energy is very, very high, that means that he has done more work, or he has a capability to do more work. Capability to do more work. Correct. So that is how generally our day-to-day life scenarios in which we understand this from an English sense, is that if a person has more energy, he is liable to do more work. Correctly. And these all terms are generally related to something which is called as power. So I have more power, if means if I'm able to do more work. Correct. So these all are in general sense. But when we go to physics, every concept being explained here, every word which is written here has a different meaning. Okay. Every word has a different meaning. Every word has a different unit, if we say in more physical terms. So let us try to understand this from the very basics, as in what these words actually mean. Okay. So the terms work, energy, and power are frequently used in everyday language. So let us say a farmer is plowing the field. So generally, amount of work required. So basically, what we can say in general sense in everyday language. So let us say if I'm doing some work, if some work is being done, so that can be related to, let's say, sweating. Sweating is being performed. So these are things we are generally observed. Let us say if I'm working very hard. So if someone is working very hard, what is the basic sense? What is the basic sense? That yes, he's working hard. That means he's sweating. Let us suppose. Then his legs are paining. Let us suppose. Okay, so these are the general sense in which we observe work in day-to-day life. Okay, so farmer plowing the field, then a construction worker is carrying bricks. Okay, so basically how is carrying bricks is being done? Let us suppose there is a complete stack being kept up here, right? And then a person is standing here. He keeps this brick over, let us suppose, his head, and then it moves from one position to another position. Then he comes forward, then it comes backward, takes another brick, keep up in his head, and then again goes here. So this is the to and fro motion, and this is how a work is being done. Work is being done by construction worker also. Okay. The next thing is students studying for a competitive exam. That is also a work only. If you are studying, if you are playing, everything comprises of doing work. You are studying, you are playing, right? You are watching something. Everything is a work. The amount of extent of physical activity may be differing in each of these scenarios, but everything is comprised under work only. Okay. An artist painting a beautiful landscape are all said to be working. Okay. So in some case scenarios, let us suppose if you are taking farmer plowing the field, the amount of physical work or physical activity is very, very high. Correct? So he has to even physical activity is very, very high for this work. Correctly. So basically he has to use his legs also. He has to use his hands also. Correct. Then he has to keep observing the surroundings that the work is being completed or not. And or let us suppose if a person is artist is painting a beautiful landscape, then generally hands are only required. He may sit and do the work. Correct. So these are all the different types of usage of the word work in our everyday language. Okay. Now let us move forward. Fine. So in physics, however, the word work covers a definite and the precise meaning. Okay. So we will have a complete definite meaning. We will understand this definite meaning. That is the majority of this complete chapter, which will be working upon. So somebody who has the capacity to work 14 to 16 hours a day is said to have a large terminal energy. So as I already already explained to you, let us say if a person is doing a workout, correct? Let us say he's doing a workout from, let's say 6 to 8 a.m. correctly. So what generally people observing from outside will say that this guy has a very high energy, and that's why he can do a large amount of work. Correct? So generally what people say, people relate energy with work here. Okay, so this is the amount of energy basically refers to the amount of nutrients you have in your body, correct, or energy you have in the body. So this is generally referred to the energy in body, correct, or here generally in human's body. That is how we refer to work in everyday language. Okay, but in physics, as it is written here, that the word work has a or covers a definite and the precise. Okay, so let's move on. So we admire a long distance runner for her stamina energy. Quite evident. Again, energy is being used here. So basically, a human or a runner will have a very, very high energy. All right. Or in general terms, as per runner, in terms of runner, we generally say that the person's stamina is very, very high. Correct. This can be linked to the amount of capacity which the lungs can offer to him. Correctly. So so again, if stamina is high, we say that the person's energy is very high, and hence if the person's energy is very high, we say that the amount of work he does is again high. Correct. So again, the human's energy is being explained or related to the work. Okay. Again explaining. So this is basically everything is being explained in everyday language, how we refer to work being done. Okay. Fine. Moving on. So energy is thus our capacity to do the work. Okay. So how we encapsulate energy or how we understand energy? Energy is basically the capacity to do work. So it's quite evident. If I have zero energy, then I cannot do any work. Correctly. So in general case scenarios, there are many instances when we don't have any energy, and that's why we go to eating. Correct. So sometimes it is generally said that eating provides you energy. So relating to that, our energy gets increased, and therefore if energy gets increased, we are able to do more work. Correctly. So that is how energy is related to work. So therefore it is written here that energy is thus our capacity to do work. Fine. Now in physics too, the term energy is related to work. It is related to work. Please look over this line very carefully. It is related to work in this sense, but as said above, the term work itself is defined in much more precisely. So it is defined much more precisely, which is the introduction, or this is the basic agenda of this chapter. Fine. So that thing being said, this complete slide just depicted us to understand the word work and energy in a more general sense. So basically, what do we understand by the words energy and work is being explained here, which is being explained in our everyday language. Now in the subsequent slides, we'll understand what actually the words work and energy mean in physics. Okay. Fine. So moving on more. So now let us understand power also. So basically the word power is used in everyday life with different shades of meaning. So different meanings are there for the word power, right? So in karate or boxing, we generally say it as powerful punch. So let us suppose there is a person who has more power. So what does it mean? So if I have more power, then I can give more powerful punches, correct? So generally saying, let us say you are offering or you are watching a WWE match. Then there are two persons who are fighting against each other, and if one person offers a very big blow to the other person, generally the terms which come out of our mouth are, he has a great power. We won't say he has a great energy, or we won't say he has a great work being done, correct? So that is how we generally analyze, or we generally utter the words refers to power here and not work and energy here. So you can refer that our brain itself can understand when do we use the word power, when do we use the word work, and when do we use the word energy, right? So again, generally speaking, so whenever generally increase in power or greater power refers to, let's say in sports like karate and boxing, to powerful punches. Okay. Moving on, these are delivered at a great speed. That's fine. So this shade of meaning is close to the meaning of the word power, which is used in physics. Okay. So just now this is just everyday language word. We will understand what is basically power in the subsequent classes. Okay. We shall find that there is at best a loose correlation between the physics definition and the psychological pictures these terms generate in our mind. So this is a very important line. That is, the actual meaning or actual English meaning, which we understand from the words work, energy, and power, are somewhat related to them, but not completely. When you will understand, when this chapter will be completed, this has to be one of the main agenda of this chapter, so that you can understand the difference between the actual meaning, which we generally refer from the picture, that is psychological pictures, and the physics definition. Okay. Fine. So this is just that is why it's an introduction, so that we can understand that the words work, energy, and power all are different terminologies in physics. Okay. Fine. So the aim of this chapter is to develop an understanding of these three physical quantities. And before we proceed to this task, we need to develop a mathematical prerequisite. So basically, we will understand the vector agenda here. Okay, so again, vector, our best friend, will be utilized here. So we started using vectors when we were a small child with motion in a straight line. Then we increased it to 2 dimensions and used it for motion in a plane. Correct. And then we again used it for laws of motion, in which I understood the Newton's first law, second law, and third law. And now again, our best friend is here with us again, so we will use it for our work, energy, and power concepts also. Okay. So this time only vector addition and subtraction won't be of much help. We need to multiply the vectors here. And that is why, if you see clearly, a word is written that is a scalar product of two vectors. We will understand what is basically this scalar product written. Okay. So just again iterating the last statement. So before we proceed to this task, we need to develop a mathematical prerequisite. What does it mean, mathematical prerequisite? It simply means that you should have a mathematical understanding of some of the mathematical terms, here basically vectors, before starting the concepts regarding your work, energy, and power. So what are these basically? They are basically the scalar product of two. Right? Okay. Moving on, now let us understand first of all the scalar product, and then we can move forward to the different examples. Okay, so before starting scalar product, let me just revise you the concepts of vectors which we have understood in the previous chapters. So vector, okay. So first of all, let me define vector again. So vectors are quantities which have both magnitude and direction, which follows triangle law of addition and parallelogram law of addition. Okay, so this is the basic definition of vectors. Examples of vectors, if you can refer to, so it will be easy. So if you can remember, if you can recall as I'm explaining you, that means you are also going along with the complete flow. You can understand each and every concept in physics very clearly. Okay, so examples of vectors. So first example can be your displacement. Then next can be your velocity. Then next can be your acceleration. And next can be your force. So these are all the concepts generally which we have referred till now. As the chapters go on, we will understand more and more vectors more clear. Okay, so this is a definition of the force. Then how to do the vector addition and vector subtraction. So then we understood two different concepts. So one is vector addition. So let us suppose this is some vector A, this is some vector B. Therefore, the resultant will be this. That is from the tail of A. If the from the tail of A to the head of B, if we join it, so that will be the resultant, which is equal to A plus B. Correct? Also, second was your vector subtraction. How was vector subtraction being explained in terms of your graphical method? Let us suppose you need to do let us suppose you need to do A minus B. So that can be said as equal to A plus minus B. Okay. How to solve it graphically? Let us suppose this is your A. Let us suppose this is your B. Let us suppose this is your B. Then we change it into minus B like this. And then simply do, this is your A. This is your minus B. Therefore, this will be the resultant. Let us say I denoted by P, which is equal to nothing but A minus B. Okay. Then we also find the analytical method to find out the vector addition. So the answer came out to be under root of A square plus B square plus 2AB cos theta. Fine. So that is the complete revision of the vectors which we understood in the chapter of motion in a straight line and motion in a plane. So that thing being said, let me just erase this and let us understand now the future discussion regarding this chapter regarding vectors, which is your scalar product. Okay. So we know vector addition, we know vector subtraction. Let us now understand scalar product of vectors. So why I'm again and again iterating scalar product? Because the vector multiplication is done in two types. There are two types of vector multiplication. One will be explained here, the another will be explained in the subsequent chapters. Okay, so we'll go very slowly with the concept of vectors. We'll just add single thing as well as we move. Okay, fine. So let's start understanding whatever is written here. So we have learned about vectors and their usage in the chapter motion in a plane, right? Then physical quantities like displacement, velocity, acceleration, force, etc. are vectors. Correct. We have learned how vectors are added or subtracted. Correct. Now we need to know how vectors are multiplied. So now let us understand how. So let us now understand how these vectors are multiplied. Okay. So there are two types of multiplying vectors, as I just explained to you. So there are two types of multiplying these vectors, which we shall come across. The one way is known as the scalar product. It gives a scalar from the two vectors, and the other is known as the vector product, produces a new vector from the two vectors. Okay. So just explaining you the meaning of both of them. We will go with the understanding of only one. I won't go into, because understanding of both right now will create confusion. That's why we'll go one by one only. Okay, so let us understand just the meaning of both of them, move forward with the one. When the time comes, we will understand the second one also. Okay, so vector multiplication. Fine. So vector multiplication are of two types. One is called as scalar product, another is called as your vector product. So what can you understand from the name? So as you go on with the physics, this is my general understanding which I have studied in these complete lectures, that whenever majority of the concepts names can be understood from the word itself. So what does this line say? This line says it is scalar product. So from the word product, it can be understood that it's a multiplication here. Similarly, from the word vector product, it can be understood that it's a product, that means it's a multiplication here. Now the first line says that first word says that it's a scalar, and here the first word says it's a vector. Okay, so basic meaning of scalar product is that the answer or the output you produce from this is a scalar quantity. That's it. That's the meaning, and that's the difference between your vector multiplication of scalar product and vector. Similarly, here the output which will be produced after multiplication will be a vector quantity. Fine. So that is the only difference between the scalar product or vector product, or that is the comparison between scalar product and vector. Fine. That thing is only written here also. So one way is the scalar product, which gives a scalar from two vectors, and the other is known as the vector product, which produces a new vector from the two vectors. Okay, fine. That thing being said, now let us understand the scalar product and move forward. Okay, so here we take up the scalar product of two vectors. Okay, so let me just first explain to you and then we can move forward. So scalar product of two vectors. Okay, so what is scalar product of two vectors? The scalar product of two vectors is written like this. Let us say this is your vector A and this is vector B. If I need to do the scalar product of two vectors, it is equal to A dot B. A dot B. Okay, which is equal to the magnitude multiplication of A multiplied by magnitude multiplication with B into cos theta. Okay, this is nothing but your scalar product of two vectors. Quite easy to understand right now. Scalar product is easy. Only a little typical is your vector. Won't go into detailing of that. And understanding it again. Let us suppose this is the vector A in this direction. Let us suppose this is the vector B in this direction. Okay, this is the angle theta between them. What is the magnitude of A? This length will be nothing but the magnitude of A. Let us say I write it like this. What is the magnitude of B? The magnitude of B will be nothing but this value till here. Correct? Therefore, what is dot product or scalar product? It is called as A dot B, which is equal to magnitude of A multiplied by magnitude of B multiplied by cos theta, where theta is the angle between both. Fine, quite easy to understand. Let's understand whatever is written here now. For the scalar product or the dot product, so it is also called as dot product. For the scalar product or the dot product of any two vectors A and B denoted as, so how are they written? It is written as A dot B. If you remember correctly, when we have started with the understanding of the chapter motion in a plane, generally we can write either as bold letters, as vectors as bold letters, or you can just write the vector A with a bar sign above. Okay, so vector representation is being explained here. So you can refer to here also that vector is being represented in bold letters. Okay, so A dot B, which is read as A dot B, is defined as nothing but A dot B, which is equal to multiplication of A into B into cos theta. Fine, so that is the scalar product of two vectors. Fine, let's move on. So where theta is the angle between the two vectors as shown in the figure A. So as you can see clearly that this is vector A, this is vector B, and this is the angle theta between them. Okay, moving on. So since A, B and cos theta are scalars, correctly? A is also a scalar, B is also a scalar, cos theta is also a scalar. The dot product of A and B is a scalar quantity. Explain it again. So what we know from the previous definition of scalar product, we know A dot B, the definition which we just understood in the previous slide, is equal to magnitude of A multiplied by magnitude of B multiplied by cos theta. Now see clearly, this is a scalar, correct? This is again a scalar, and this is again a scalar. So if all these are scalar, then this output will be a scalar quantity, and that is how the name is the scalar product. Okay, so you can understand how does a name can refer to the original concept or methodology being worked upon it. Fine. Okay, let's move forward. Now each vector A and B has a direction. Quite clear. We know that each vector A and B has a direction. You can see that this is the direction of A, and you can see that this is the direction of B. Correct? But their scalar product does not have a direction. Quite clear. We know that scalar quantities are those quantities which have only a magnitude and no direction. Right? I will just write it here also. So what are scalar quantities basically? Quantities which have only magnitude and no direction. Clear? So that is why, as it is saying that scalar quantities are those quantities which have only magnitude and no direction. Therefore, the scalar product, as we understood just now, that scalar product is a scalar quantity, therefore it will not have a direction, but these vectors A and B will have a direction. Okay, so basic sense is something that the components of LHS are having basically directions, but the output of this RHS is not having any direction. Okay, fine. Moving forward, so from the above equation we have A dot B. Okay, so let me explain this again. So let me just clear everything. Okay, so now what we understood from the scalar product is that is A dot B is nothing but equal to magnitude of A multiplied by magnitude of B multiplied by cos theta. Correct? We can also write this as equal to nothing but A into in brackets B cos theta. Correctly? We can also write, because multiplication has this property with it. We can also write this nothing but A cos theta multiplied by B. Let us now try to understand this equation, what is happening here. Okay, so for more conceptual clarity, we will be working with the rectangular coordinate system, and more clearly, because z direction is unknown here or z direction is not required here, we will be working with only xy plane. Okay, so let us suppose that this is the xy axis, this is your x axis, this is your y axis, and let us suppose that A is in this direction, which is along the x axis. A can be in any direction. Just for more clarity, more simplicity, I explained A in the direction of x. Okay, and let us suppose B is in this direction. Okay, with some magnitude, or sorry, not magnitude, with some angle theta. Correct? Now using simple trigonometry, I will just resolve the components of your B. So therefore, this will be resolving like this, and similarly resolving like this, right? So it will be tilted here only. This will be equal to nothing but B cos theta. So I'm sure you are now quite clear, as in you can directly find out the values of B cos theta and B sin theta. If not, just form a triangle very quickly. Okay, let us say this is your B. You just need to find this value and this value. So how to find it out? Let us say I denote this value as your height, and I denote this value as base. Then what is your cos theta? Your cos theta is nothing but base upon value of B. Therefore base is nothing but equal to B cos theta. And similarly sin theta is nothing but equal to height by B, and therefore height is equal to B sin theta. Correct? That is how you can understand how base is equal to B cos theta and height is nothing but equal to B sin theta. Okay, fine. So this is nothing but so these concepts should be in your head directly, so that if you see an angle, if you see a vector, you can directly resolve into two components. Okay, so just try to do more and more practice, so that at least you can directly resolve the components into B cos theta and B sin theta. Okay, fine. So now let us go further the discussion here. So what can we understand from this equation here? Okay, so this is nothing but A, the magnitude of A is multiplied with B cos theta. That means that if we resolve the component, let me write, so that will be much easier. So if we resolve the component of B in the direction of A, then what can we write? A dot B is nothing but equal to magnitude of A multiplied by resolved magnitude of B in direction of A. Correct? So what was the magnitude of A? Magnitude of A was nothing but A only. And what is resolved magnitude of B in direction of A? It is nothing but B cos theta. So I hope you can understand this line here clearly. So it is nothing but A into resolving of the vector of B, which was in the direction of A. Now let us try to reverse the situation here. Okay, let us try to reverse the situation here. So now what will happen? What does the second line tell you? So that I need to change the graph also. Wait. Okay. So now what is happening this time? Let us suppose I took this as x-axis, this as y-axis, and this was my b now. Okay, this was my direction of b. Let us suppose, and this was my a. Okay. So if this was my b and this was my a, as we know that this is nothing but your angle theta. Resolving the components again. So resolving it here will lead to one angle here. The component of vector here, one component of vector here. So again, please see clearly. So if this is angle A, then this will be nothing but A cos theta. Correct? Because angle A has been resolved in this direction. Therefore, this will be A cos theta. Similarly, this will be your A sin theta. Okay. So now let us understand this using the equation number 2. So what does equation number 2 gives us? The equation number 2 simply gives us that the scalar product A dot B is nothing but equal to magnitude of B into magnitude of, or we can say resolved magnitude of A in direction of B. Fine. So I hope it is clear to you. So it is nothing but your magnitude of B into resolved magnitude of A in direction of B. Okay. So that is how we can understand this scalar product in these terms, that it is nothing but if we have some vector A, if we have some vector B, then if I can just resolve the component of B in the direction of A and multiply the magnitudes of both these components, then I can get the scalar product from that result also. Okay. Achha. Now one thing more, just one discussion more, and then we can move forward. So here, if you look very clearly, in the starting I said that for simplicity, I either put A in this direction, or in the second case I put B in this direction. But you may ask that what if I cannot do this in this direction? Correctly, it will not occur every time that A will be in the direction in x-axis or B will be in the direction, let's say, y-axis. So it was just for simplicity terms. Even if you put A in this direction, correct, and even if you put B in this direction, then also how we resolve the components. Let us say this is your B. How we resolve the components? We just put perpendiculars from here. Then this will be nothing but your B cos theta, and this will be nothing but your B sin theta. Okay. So just for more vision clarity, I explained it using the straight terms. Even if the vectors A and B are not aligned with x and y axis, then also the answer refers to same only. So it is again, what is the scalar product? Is nothing but this B cos theta multiplied with the magnitude of it. Okay. So I hope this thing is clear. So let us move forward now. Okay. So from the above equation, we have A dot B is nothing but equal to A multiplied by B cos theta, which is also equal to B multiplied by A cos theta. Okay. Geometrically as in if you try to project it graphically. So geometrically what happens is that B cos theta is the projection of B onto A. Quite clear? So B cos theta is a projection of B onto A, right? In figure B, as you can see clearly here, so this is nothing but the explanation which I just did in front of you. And A cos theta is a projection. So you can see here, so A cos theta is a projection of A onto B, right? So it's of A onto this B line, and similarly projection of B onto A here. Okay, moving forward. So A dot B. So A dot B is the product. A dot B is the product of the magnitude of A and the component of B along it. Or in other words, what we can say alternatively, it is again the product of magnitude of B into the component of A along B. Okay. So the first line is nothing but explaining this line here, that is A into B cos theta, and this alternatively line is just explaining you the second line, which is B into A cos theta. Okay. So I hope it is quite clear to you that what is the actual meaning of scalar product. Okay, so I think you are now very strong with the initial basic understanding of scalar product. Okay, so what is it basically? It is nothing but denoted as A dot B, which is nothing but equal to magnitude of A multiplied by magnitude of B into cos theta. Correct? It can also be written as nothing but magnitude of A into magnitude of B. It is just a representation. Okay, so magnitude is written like this, as mod into B cos theta. Also, it can be said as magnitude of A into cos theta into magnitude of B. Okay, so this is nothing but the understanding of your scalar product of two vectors. Okay, fine. That thing being said, now let us move forward. Okay, now let us understand some of the properties of scalar product. Okay, so what was the definition again? So definition was nothing but A dot B is equal to A B cos theta. Correct? Now, even if I find, let us now find B dot A. What will be B dot A? B dot A will be again A B cos theta. Now, if you look clearly at the equation number 1 and equation number 2, as RHS of both are same, therefore what we can say? We can say that A dot B is equal to B dot A. Right? So what is this property called? This property is nothing but commutative law. Therefore, scalar product follows the commutative law. Okay? I hope it is clear. This is the first line explained here. Okay? So above equation, that is A dot B is equal to AB cos theta, shows that the scalar product follows the commutative law. Okay, that is A dot B is equal to B dot A. Okay. Next thing is scalar product obeys the distributive law. Let us try to understand distributive law now. Okay, so it is nothing but A dot B plus C. Okay, so A dot B plus C is nothing but equal to A dot B plus B dot, sorry, A dot C. Okay, so simple multiplication. So it is nothing but this multiplied by this plus this multiplied by this. Okay, so scalar product also obeys the distributive law. Fine. Next thing is further lambda A dot lambda B is equal to lambda A dot B. Okay, so this is another property, that is the product of lambda A with lambda B is nothing but equal to lambda A dot B. Okay, so this is the third property being explained here. Okay, so we know that scalar product follows the commutative law. It also follows the distributive law. And now this is the another property, that is lambda A dot lambda A dot B is equal to lambda A dot B. Okay, where lambda is a real number. Fine. So that thing being said, now let us understand the next concept, that is for unit vectors. So before understanding unit vectors, let me just revise unit vectors again. So what are unit vectors basically? Unit vectors are those vectors which have unit magnitude. What is the meaning of unit magnitude? That is, the magnitude is 1. Which have unit magnitude equal to 1. And the direction is along the vector asked or specified, along the vector specified. Okay, so let us suppose take a very general case. For example, if this is your vector A, right, then the magnitude of this A will be magnitude of this will be this, right? So what is the unit vector? Unit vector, if I need to find out the unit vector for this vector A, and that unit vector denoted unit vector, let's say denoted by n cap, is nothing but equal to this vector A upon magnitude of vector. So that is how you can understand the unit vector concept. Okay. Then some general examples of unit vectors which we consider. So general examples of unit vectors used are I, J, K. Where are they used? let us say I make an XY Z coordinate axis, then X I cap is along this direction, Y cap is along, J cap is along this direction, and similarly the K cap is along this direction. Okay, so that is how we understand I, J and K. Fine. Okay. That thing being said, now let us understand this fourth property regarding the unit vector. Okay. So this thing is being explained. This thing is being explained. This thing is being explained. Now let us try to understand this one. Okay. So what is the first line written? It is written scalar product of I into I. Okay. This is nothing but magnitude of I multiplied by magnitude of I multiplied by angle between both of them. If you refer to this line very clearly, I cap and I cap will be in the same direction. Therefore, the angle between them is equal to 0 degrees. Correct? Therefore, I cap dot I cap, you know what is the magnitude of I cap? It is 1 multiplied by 1 into cos of 0 degrees, and we know what is cos of 0 degree? It is 1. Therefore, we got I cap dot I cap is equal to 1. Similarly, J cap dot J cap is nothing but equal to magnitude of J cap into magnitude of J cap into cos of, again, 0 degree, which will be equal to 1. K cap dot K cap is equal to magnitude of K cap into magnitude of K cap into cos of 0 degrees, which is again equal to 1. So therefore, we understand this line clearly here. That is I dot I is equal to J dot J is equal to K dot K is equal to 1. Right? So this is again a scalar product of scalar product of unit vectors. Okay, this is also the same, but these are for the same vector and this is for different vectors. Now let us understand the below equation written here. Okay, so what is written? It's I dot J. So what is I dot J? It is nothing but magnitude of I into magnitude of J into cos theta. Correct? So if you remember correctly, let us say this is your x-axis, this is your y-axis, this is your z-axis, this is unit vector I cap, this is a unit vector J cap, and this is a unit vector K cap. Okay, so you can see what is the angle between I and J. If you see correctly, the angle between I and J is 90 degrees. Okay, so therefore here theta is equal to 90 degrees. Why? Because I cap and J cap are perpendicular to each other. Okay, hence what we can write? We can write I cap dot J cap is equal to what is the magnitude of mod I and mod J? It is 1 only, so it's 1 into cos of 90 degrees, and we know what is cos of 90 degrees? It is equal to 0. Therefore, I cap dot J cap is equal to 0. Okay, so I think this new concept is clear. Let us try to devise this whole situation for the remaining parts also. So it is nothing but J cap dot K cap is equal to magnitude of J into magnitude of K into cos theta. Again, J and K are perpendicular to each other. Therefore, this will be equal to 1 multiplied by 1 into cos of 90 degrees. What is cos of 90 degrees? It is equal to 0. And this will also be equal to 0. Also, K cap dot I cap is equal to magnitude of K cap into magnitude of I cap into cos of theta, which is equal to again 1 multiplied by 1 into cos of 90 degrees, which is equal to 0. Fine. So hence the second equation is also proved, that is I dot J is equal to J dot K is equal to K dot I is equal to 1. One more thing I just need to add in this. So here I dot J is also equal to J dot I, right? How it is? Because of commutative law. So even if you do I dot j or j dot I, the answer would be same. So I dot j is equal to j dot I. Similarly, j dot k is also equal to k dot I. So these things are generally known, but I'm just adding them so that we can understand, even so that a new, if k dot I is being referred somewhere, or let's say, sorry, it's k dot j. If k dot j is referred somewhere, we may not get confused as in what to do, so that we can, our mind always remembers the commutative law, the distributive law, so that only I'm making this as an exercise, but we can understand that yes, these unit vectors can also have properties of commutative laws. Okay, so j dot k is equal to k dot j, and similarly k cap dot I cap is equal to I cap dot k cap. Fine, so that is the complete understanding of your I dot j, or the complete understanding of the scalar product. Okay, fine. So that thing being said, let us move forward. So before moving forward, we will just do a quick revision of everything which we have completed till now. So first of all, we understood the scalar product. So scalar product is nothing but equal to a dot b, which is equal to ab cos theta. Okay. Next thing which we understood is that this can also be written as equal to a dot b, which is equal to a multiplied by b cos theta in brackets, and also equal to b multiplied by a cos theta in brackets. Okay. Next thing which we understood was that it follows the commutative law. What is commutative law? Basically, that is a dot b is nothing but equal to b dot a. It also follows the distributive law. What is basically distributive law? It is a dot b plus c is equal to a dot b plus a dot c. It also follows this particular relation, that is lambda times a dot lambda times b is nothing but equal to lambda into a dot b. And then we just proved these all different relations. That is, the scalar product of the same unit vector will give you 1, but different vector will give you so this will be 0. So it is, that is written 1, I don't know. This will be 0. Sorry for the mistake. This will be 0. Okay, because cos 90 is being involved, therefore this will be 0. This is 0 here. Okay, fine. Okay, now let us move forward. Okay, so given two product a is equal to so now what is being done here, you can understand this. We have understood this concept very clearly in the concepts of motion in a plane, or basically the resolution of vectors. So we know that the resolution of vectors. So let me just, as the time is completed, let me just revise the concept of resolution of vectors, and then we can move with this discussion in the next lecture. Okay. So what is basically resolution of vectors? It is being said that let us suppose there is some vector a. Okay, and there is some vector small a, and there is some vector small b. Then, according to resolution of vector, it is said that this vector a can be written as nothing but sum product of this vector a and b. That is multiplied by lambda, and this is multiplied by mu. Okay. To generalize this, how to make it more simple, what were the things which you understood? That this vector a can be resolved into components along the unit vectors, that is I and j. Correct? What were the components being involved, or what were the components along the x and y direction? We denoted them as ax and ay. Correct? So how can that be implemented? Explained here. So let us suppose this is some vector x and y plane. Correct? This is that vector a. So if you drop the components from here and drop the component from here, then this is nothing but ax, and this is nothing but your ay. Okay. Now this was in 2D plane or 2D space. Correct? This was in 2D space. Now if we just increase it to 3D space, then this a bar can be written as just the summation of 3 different vectors. But what will the unit this time? It will be ax, ay, and az. Okay. So that thing being said, that is how we understood the complete concept of resolution of vectors in the previous chapters, and that has only been explained here. Fine. So that was just a simple revision of how these vectors are being represented here. We will understand this concept from this point onwards in the next lecture. Okay. So let me stop it here only. So right now in the course, right now in the course progress, we are in the chapter of introduction only, in which we are understanding the scalar product. And after the complete understanding of scalar product, we will move on to the next point, that is notions of work and kinetic energy. That is the work energy theorem. Then we will understand work, kinetic energy, and etc. And then we can move forward. Fine. So that thing being said, thank you for listening for this lecture. We will meet in the next lecture. So thank you so much.